We tend to think about systems as these smooth, continuous things, right? Like water flowing through a pipe or a car smoothly accelerating. But the truth is, so much of our world, especially our modern technical world, just doesn't work that way. It works in clicks, in steps, in jumps. These are what we call discrete event systems, and believe me, they are absolutely everywhere.
So that leads to the big question, right? How in the world do you manage or even begin to control a system that's all about these sudden distinct actions? Your usual math, your calculus, it just won't cut it here. You need a completely different way of thinking, a whole new kind of logic, and that's exactly what we're going to unpack.
Okay, think about a classic factory assembly line. A part lands at a station, that's one event. A robot does its thing, that's another event. The part then moves on. See? It doesn't flow like a river. It lurches forward in these very clear, very countable steps.
Or what about the digital world we all live in? Every time you click a link, you're sending a request to a web server. That server has to grab the request, process it, and send the data back. Each one of those is a single event, and that server is juggling thousands of them every single second.
And this scales up to absolutely massive systems, like an entire city's traffic grid. It's just this incredibly complex dance of cars starting, stopping, and waiting, all driven by these discrete events. The point is, this jumpy kind of problem, it's everywhere you look. So how do engineers and computer scientists actually get a handle on this jumpy reality? Well, they use this surprisingly elegant and visual tool, kind of like a blueprint for actions that lets them map out and hopefully control all that chaos. It's called a Petri Net. And honestly, the best way to think about it is like a game board. It's got pieces, it's got rules, it's got moves. It lets us play out the flow of events so we can spot problems like a total system gridlock before they ever actually happen. And what's amazing is that this entire game is played with just 4 simple kinds of pieces. First up, you've got places. Those are the circles. They represent a condition, like server is idle. Then you have tokens, the little dots. These are your resources, maybe a person or a piece of data. The bars are called transitions, and that's where the action happens. And finally, you have arcs, the arrows, which are just the rules connecting everything. That's it. With just these 4 things, you can map out ridiculously complex systems. Okay, let's actually build one right now. Super simple, moving furniture. We start with our resources, our tokens, desks, and people, all sitting in a place called Room A. Now the rule, our transition, says that to move a desk, you need 1 desk token and 2 people tokens. As soon as those conditions are met, that action can fire, and poof, it basically eats those tokens from Room A, and they reappear over in the new place, Room B. So you see, it's not just a static drawing, it's a dynamic model that actually runs.
Okay, but hang on. This is where it gets really interesting. Just because an action can happen doesn't mean it will. What if you have 2 people? They could team up to move 1 big desk, or they could each move a chair separately. See, now you have a choice. This introduces conflict into the system, which is what allows Petri Nets to model all the complex decision-making that happens in the real world.
All right, so we've got the sequence of events down. We can even handle choices. But what's missing? In the real world, things take time, right? Moving a desk is not instantaneous. To make our little game board actually useful, we have to add a clock.
And there are basically 2 flavors here. A simple, logical Petri Net just tells you what can happen next in the sequence. But a timed Petri Net, now that tells you when it can happen. This is a huge leap because now we're modeling the actual delays and holding times that make or break real-world systems.
And what's so cool is how flexible this is. You can attach time to the action itself, saying, this move desk action takes 5 minutes. Or you can attach it to the condition, like a part has to wait in quality check for at least 10 minutes. Both are really powerful ways to capture how things actually work.
Okay, this is where things get a little hairy at first. Once you add time, trying to analyze these systems gets really tricky. The math can look pretty scary, but there's an incredibly clever mathematical trick that makes it all fall into place. A totally different kind of math.
So let's say you have a simple train system. The equation for the next departure time looks something like this. It involves addition, sure, but it also has this max function. That max is crucial. It basically says the train can't leave until the later of these 2 things happens. It's waiting for everything to be ready. And that max function is what makes the math an absolute headache.
I mean, that's for 2 trains.
Imagine trying to solve this for a city's entire transit system or a global supply chain with thousands of moving parts. All those max functions would create this nightmarish web of possibilities. How could you ever predict how a system like that is going to behave?
Well, the answer is this absolutely beautiful, kind of magical thing called max plus algebra. It's like we step into this alternate mathematical universe where the rules are just different. And they're different in exactly the right way to make these problems simple.
So here's the trick, and it is brilliant. In this special algebra, you just redefine the operations. The max function, the thing that represents weighting, you decide to treat it like addition. And regular addition, the thing that represents how long a process takes, you treat that like multiplication. You just change the rules of the game, and suddenly the whole problem looks completely different.
And what happens when you do this? It's just incredible. That messy, complicated equation full of max functions, it transforms into a clean, simple, standard linear equation, the kind of thing we've known how to solve for ages. This means we can suddenly use all the powerful tools of linear algebra to understand these super complex, jumpy systems. It's a truly elegant, almost magical solution.
So, a bunch of weird math, right? Why should you care? Because this isn't abstract at all. This is the stuff that is running the world around you right now. These are the unseen orchestrators of our entire modern life.
And I mean it. We're talking about the invisible engine behind global supply chains, making sure your packages arrive on time. It's in automated factories, computer network protocols that make the internet work, and public transport schedules. Heck, even the simple logic inside a vending machine can be designed and perfected using these exact same ideas.
And you know what's wild? This whole foundational idea, the Petri Net, was dreamed up by a guy named Carl Adam Petri way back in the 1960s. It just goes to show you how a really powerful fundamental insight can grow to become the backbone of so much of our world. So the next time you're stuck in traffic or you're watching your pizza delivery get tracked online, just remember what's happening under the hood. That series of stops and starts, which feels kind of chaotic, probably isn't random at all. There's a very good chance there's an elegant blueprint, this hidden logic orchestrating that whole dance.
So it really makes you think, doesn't it? What other complex, jumpy systems are out there in your day-to-day life? From the line at the coffee shop to the flow of information on your social media feed that are secretly being managed by this powerful and hidden logic.